Today, we are diving deep into the science of what is, without a doubt, our planet's most important resource, water. And to kick things off, I want to start with a single number that really shows you why this matters so much.
33%. Just let that number sink in for a second. It might not seem like much on its own, but it points to one of the greatest challenges of our time. And it's the whole reason the science we're about to talk about is so incredibly important.
Because that's what it means. A third of all people on this planet. That fact right there, it's staggering. And it's exactly why we need to get a handle on our water systems. And, the science that helps us do that, well, it has a name.
Hydrology. It's the field that studies, well, everything about water, where it is, where it's headed, and how we can possibly manage it for everyone. This is how we even begin to tackle that 33% problem.
So, to really get a grip on hydrology, we first need to zoom out and look at the big picture. I mean, how much water are we actually talking about here?
We all call Earth the blue planet, right? But this chart tells a kind of shocking story. See that huge chunk? 97.5% of all water is salt water. Can't drink it. Of the tiny sliver left over, just 2.5%, most of that is locked up in glaciers and ice caps. So when you get right down to it, less than 1% of all the water on Earth is actually fresh and accessible for us to use. Less than 1%.
And here's the real kicker. The amount of water on Earth, it never changes. We're not getting any more delivered. Every single drop we have right now is all we're ever going to get. It just moves around and around in this massive planet-sized recycling system.
So how exactly does all that water move? Well, let's pop the hood on the engine that drives it all, the hydrologic cycle.
The sun, that's the powerhouse for this entire system. All that solar radiation beaming down provides the energy that gets the whole process started. Seriously, without the sun, the water cycle would just grind to a halt.
So, that solar energy warms up the surface of oceans, lakes, you name it. This heat causes the liquid water to turn into a gas, water vapor, and it rises up into the atmosphere. This is the first huge step, evaporation.
Okay, so once that water vapor is up in the atmosphere, it starts to cool down and condense, forming clouds. And eventually, good old gravity takes over and pulls it back down to Earth as precipitation. Rain, snow, sleet, hail, the works.
Now, when that water finally hits the ground, it doesn't just do one thing. It actually has a few different paths it can take. Some of it gets caught by trees and plants. Some of it soaks right into the soil, which we call infiltration. If the ground can't absorb any more, it just flows over the surface as runoff. And then, some is actually sucked up by plants and released back into the air as vapor, a process called evapotranspiration.
And this is the perfect way to think about it. It isn't a straight line from A to B, it's a constant loop. Water evaporates, it precipitates, it flows, and then it starts all over again. No real beginning and no real end.
So we've got this massive global cycle. But how do scientists actually measure and manage water at a local level? I mean, you can't work with the whole planet at once, right? Well, that's where the hydrologist toolkit comes in.
They start by focusing on a much more manageable area called a watershed. The easiest way to picture it is like a giant basin or a bowl. Any rain or snow that falls inside the edges of that bowl eventually drains down to a single point, like a river or a lake. This becomes the basic building block for all their work.
And inside that watershed, hydrologists use a concept that's actually surprisingly simple. It's called a water budget. And honestly, it works just like balancing your bank account. What comes in minus what goes out equals the change in how much you have left.
Let's break it down. Your inflow is the water coming into the system. That's mostly rain and snow. Your outflow is all the water leaving, whether it's through rivers, evaporation, or seeping into deep groundwater. And the difference between those two tells you if the amount of water stored in the account, in the soil, lakes, and aquifers, is going up or down. Simple as that.
Now, this isn't just some abstract theory for scientists to play with. Understanding that water budget has massive, real-world consequences. This is where the science of hydrology becomes the practice of engineering that shapes our world. I mean, just think about it for a second. The water from the tap in your kitchen, the irrigation systems that grow our food, the massive structures that protect our cities from floods, even clean energy from hydropower, all of it, every single one, is designed using the principles of hydrology. And this right here really drives the point home. A dam is an absolute marvel of engineering, but its safety, its very existence, depends completely on getting the hydrology right. Engineers have to calculate everything from the worst possible flood scenario to the average daily inflow. If they get those numbers wrong, the risk isn't just a mistake, it's a potential catastrophe.
And all of this brings us right back to where we started, looking at the huge challenges that are still ahead of us.
Look, with more and more people on the planet and a climate that's changing rainfall patterns all over the world, the work of hydrologists and water engineers is becoming more critical with every passing day. The margin for error is shrinking, and our need for smart, sustainable water management is just exploding.
So, that leaves us with one final and really important question. The water cycle itself is constant, but our world is not. The challenge for all of us is to apply this science to build a future where everyone has the water they need. The only question is, how are we going to do it?